Have you ever just looked at a bridge or a building or even the lines on the highway and thought, hey, those lines, they look parallel? I mean, we see them literally everywhere. But how can we be absolutely mathematically certain? How do we make that leap from just looks parallel to proving it is parallel? Well, that's what we're going to do today. We are going to build the complete geometric toolkit to do exactly that. All right, here's our game plan for this explainer. First, we're going to flip some logic you might already know right on its head. Then, we'll build up our toolkit piece by piece, starting with congruent angles and then moving on to supplementary ones. After that, we'll put them to the test with a real example, tack on a couple of special cases, and then wrap things up by learning how to actually construct a parallel line from scratch. Sound good? Okay, first up, flipping our logic. We've got to completely reverse the way we normally think about parallel lines and all the angles that come with them. So think about what we already know. Up till now, we've pretty much always started with one solid fact. These two lines are parallel. And from that one starting point, we could figure out all sorts of other things, right? We knew that corresponding angles had to be congruent, that alternate interior angles were also congruent, and that those same-side interior angles, yep, they'd always add up to 180 degrees. But today is the big switch. We're flipping the script completely. We are no longer going to start by assuming the lines are parallel. Nope. Instead, we're going to start with the angles themselves. We're going to use those congruent or supplementary angles as our evidence, our clues, to build a rock-solid case and prove that the lines just have to be parallel. All right, so let's start building our toolkit. The first set of tools we're going to look at all hinge on one key idea: finding pairs of angles that are congruent. And remember, that just means they have the exact same measure. Okay, tool number one is called the corresponding angles converse. And the logic here is super straightforward. If you can find just one pair of angles that are in corresponding spots and you can prove they're equal, boom, you're done. The lines are parallel. It's that simple. So let's see this in action. Take a look at the diagram. See angle 1 and angle 2? They're in the exact same spot at each intersection, kind of the top left corner for both. If you can show that those two are identical, then you can be absolutely certain that line L is parallel to line M. Guaranteed. Now, our second tool works pretty much the same way. It just applies to a different pair of angles. This one's called the alternate interior angles converse. And with these, you can often spot that classic Z shape they make. See it? They're on opposite or alternate sides of the transversal, and they're inside or interior to the two lines. So if you know for a fact that angle 2 is congruent to angle 3, it's a lock. Line L has to be parallel to line M, no question. And to round out this first batch of tools, we've got the alternate exterior angles converse. You've probably guessed it already. It's the exact same logic, but this time for the angles on the outside. Find a congruent pair on opposite sides of that transversal, and bam, you've got your proof. All right, so we've got 3 solid proof-generating tools in our kit now. Let's put them to the test and see how they work in a problem that's a little more interesting. Okay, check this out. It's kind of like a puzzle, right? We've got this grid of lines and a whole bunch of angles. For each part of the question, the real challenge is twofold. First, you've got to figure out the relationship between the angles they give you. And second, you have to pinpoint exactly which two lines and which transversal are creating those angles in the first place. All right, let's break this down. For part A, we're looking at angle 3 and angle 8. If you look closely, they're on the outside of lines C and D and on opposite sides of transversal B. That makes them alternate exterior angles. So if they're congruent, we've proven that line C is parallel to line D. Now for B, we have angles 5 and 9. These are formed by lines A and B, with line D acting as the transversal. They're in the same spot at each intersection, so they're corresponding angles. And if they're congruent, you guessed it, line A is parallel to line B. And finally, part C, with angles 1 and 8. These two, they don't really have one of those special relationships we can use. So even if we know they're congruent, it doesn't actually prove any of the lines are parallel. It's a bit of a trick question. Okay, so that's all great when angles are equal. But what happens if they're not? Well, no worries. Our next set of tools is built for exactly that situation, when specific pairs of angles add up to 180 degrees instead. So this first one is for interior angles that are on the same side of the transversal. And the key here is we're not looking for them to be equal anymore. We're looking for them to be supplementary. If you can show their measures add up to a perfect 180 degrees, then you've proven the lines are parallel. And you can probably guess what's next. The exact same logic applies to the exterior angles on the same side. If they add up to 180, the lines are parallel. And just like that, our whole set of angle-based proofs is complete. Pretty cool, right?
Okay, we're almost there. Let's add two final but really powerful theorems to our toolkit. These handle a couple of special cases you might run into.
Now, this first one is so intuitive, it almost feels like common sense. I mean, think about it. If line A is parallel to line B, and line B is also parallel to line C, well, then it just makes sense that line A has to be parallel to line C, right? It's like a chain reaction. That's the transitive property in action, but for parallel lines. And our last tool is all about right angles. It's pretty simple. If you've got two different lines and they both hit a third line at a perfect 90-degree angle, they literally have no choice but to be parallel to each other. The ladder rung analogy is perfect here. Each rung hits the side rails at 90 degrees, and that's what makes all the rungs parallel. So there we have it, a full, complete toolkit for proving that lines are parallel. But what about making one? How do you actually draw a perfectly parallel line? Let's walk through a classic geometric construction to see how it's done. So here's the classic challenge. You're given a line, we'll call it AB, and a single point P, just floating out in space, not on the line. Your mission, should you choose to accept it, is to use only a compass and a straight edge to draw a new line that goes right through P and is perfectly, flawlessly parallel to line AB. Okay, let's walk through the method. Step 1, you just draw any old line you want through P that crosses line AB. That's our transversal. Step 2, pay attention to the angle that gets created down at that new intersection. Now, step 3 is the magic move. You go back up to point P and, using your compass, you perfectly copy that angle, creating a brand new congruent angle in the corresponding spot. And this is where it all comes full circle. See what we did? By forcing those corresponding angles to be congruent, we're using theorem 2.3.1, the corresponding angles converse, the very first tool we put in our kit, to guarantee our new line is parallel. We're not just proving it, we're using the proof to build it. How cool is that? And there you have it, the complete toolkit, not just for proving, but for actually constructing parallel lines. So the next time you're out and about and you see a fence or some railway tracks, or even the pattern on a tiled floor, you'll know exactly what it would take to prove that what you're seeing is truly parallel. So now that you have the tools, I'm curious, what real-world pattern are you going to go prove is parallel first?